Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 50 on Infinite Series.
The next few lessons are at the heart of this chapter and deal with infinite series, a hopefully not too unfamiliar topic. We're going to detail specific examples and consider convergence and divergence of series in the same manner that we dealt with convergence and divergence of improper integrals.
We continue with our program of building a calculus for sequences, considering in this lesson the analog of the improper integral. These are called infinite series, something that you've seen before, but now we're going to treat them a bit more carefully. Now, how was it that we handled improper integrals? Recall, the integral from 1 to infinity of f of x dx was defined in terms of a limit, the limit as t goes to infinity, of the finite integral of f from 1 to t. So, in defining what we mean by an infinite series, that is, the sum as n goes from 1 to infinity of a sub n, we'll use the same approach. We can think of this infinite series as being something like a discretization of an improper integral. And so we can define this sum to be the limit as t goes to infinity of the sum n goes from 1 to t of a sub n. That is, the series is really the limit of the sequence of partial sums. Recall that when it comes to improper integrals, the central and subtle question is that of convergence or divergence. The same occurs with infinite series. Now, you've seen infinite series all throughout this course from the very beginning, and I have told you repeatedly, don't worry too much about convergence or divergence. We'll worry about that at the end of the course. Well, it is time to push that button. It is time for all of those worries that have been inside your head to come out, and we will deal with them. We will go through the notion of convergence or divergence slowly and carefully, giving you lots of practice so that you get good at it. Let's consider some examples of series. Some are very easy to understand. If we look at 1 plus 1 over e plus 1 over e squared plus 1 over e cubed, etc., well, we recognize this as a geometric series. So not only do we know that it converges, we know exactly to what value. On the other hand, we recall that the geometric series does not always converge. For example, if we evaluate the geometric series at -1, then one could try to argue that the appropriate value is 0, or one could argue that the appropriate convergence is to 1, or even to 1/2. None of these holds. This is a divergent series because the limit of partial sums does not exist. It oscillates. Now, some series do converge, but are so subtle in how they do so, they're very difficult to evaluate. The sum from 1 to infinity of 1 over n squared does converge, as we'll be able to show soon, but it converges to a value that is very difficult to determine exactly. That value is pi squared over 6. Some series are not so easy to figure out. Consider 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, etc. To what, if anything, does this converge? This last example is a special series that is called the Harmonic Series. Let's investigate this series a little bit. We'll fire up the computer and see what happens when we add, let's say, the first 10,000 terms together. we get a result that seems decidedly finite. It's about 9.79. But what happens if we, say, add another 5,000 terms to that? Well, our result is only a little bit bigger. We would guess that this is about to converge, since the next term in the series is 1 over 15,001. That is quite small. But let's just check it. Let's add the first 20,000 terms together. Well, we can see that we're slowing down a bit. We've only gone about 0.3 more, not even that. Still, I'm not going to be quite comfortable until I see that it's converged to several decimal places. But this does not appear to be happening, even with 25,000 terms. So let's sum up the first 100,000 terms. Surely, if this diverges and goes off to infinity, then we would see it. Well, the answer in this case is just a little bit more than we had before, but not so little as to make me conclude that it converges. So what is happening in this case? Well, we're going to have to use something beyond a calculator to determine convergence or divergence in this case. What we're going to use is our calculus intuition. The harmonic series reminds us of the improper integral, as x goes from 1 to infinity, of 1 over x dx. Indeed, we can consider that sum, that series, as a discretization of this integral, as a left Riemann sum of this integral with a uniform partition of step size 1. Now we know that the integral of 1 over x, as x goes from 1 to infinity, diverges. And we can conclude from the geometry of this diagram, if nothing else, that the harmonic series is strictly bigger. Therefore, we can conclude that the harmonic series diverges. What's wonderful about this is that we've used our continuous or smooth calculus understanding to conclude things about this discrete calculus example. This discussion raises the question, what can you trust when it comes to determining convergence or divergence? As we've seen, a calculator is not the best tool for determining convergence or divergence. What about your intuition? Maybe you should just get a feel for what works. Well, intuition is also flawed. Let's look at an example. I claim that the series 1 minus a half plus a third minus a fourth plus a fifth, etc., something that we'll call the alternating harmonic series, does converge, and it converges to a value of log of 2. Now, why is that the case? Well, recall that log of 1 plus x is exactly this kind of alternating sum of x to the n over n. If we evaluate this at x equals 1, then we obtain this value. Now, technically speaking, 1 is not in the interval of convergence for this series, but hey, trust me. You can trust me. This actually does converge. Now, if you believe that, then what happens when you multiply everything by 1/2? Well, of course, you just multiply each term by 1/2. That is definitely true. Now, if we spread those terms out a little bit and add everything together term-wise, what happens? Well, we get 1. Negative 1/2 plus 1/2 is 0. We pull down the 1/3. Negative 1/4 minus 1/4, that's a minus 1/2. Pull down the 1/5. The 1/6 cancel. Pull down the 1/7, etc. I think you can keep going with this. Some of the terms cancel, some of the terms add together. What is this series? Well, it converges, and it converges, as it must, to 3/2 log 2. That is log 2 plus 1/2 log 2. This is true. Trust me. But at this point, we grow quite concerned, because if we rearrange the terms, we get exactly what we started with. It is a fact that by rearranging the terms in the alternating harmonic series, we obtain a different answer. That means your intuition is not so good all the time. So what can you trust? And you can't even trust me. Sometimes I make mistakes. There's one thing you can trust, and that is logic. Careful, deductive reasoning. We are going to use tests for convergence or divergence that are based on logic and calculus. That is what you can trust. In general, the way that this is going to work is as follows. You'll start with some given sequence, and you want to determine whether the series converges or diverges. You'll have several, about a half a dozen or more tests to choose from. Not all tests apply to all series. So you check to see whether a given test applies. If it doesn't, choose another. If it does, then apply the test. Some tests don't work with a given series, in which case you try again. But if the test does work, then you're done. You've determined convergence or divergence. Unfortunately, you might run out of tests, in which case you fail. But that won't happen. We're going to have lots of tests. Here's the first one. This is called the Nth Term Test. And it goes as follows. It's an if-then statement. If the hypotheses are satisfied, then the conclusion follows. Here's the hypothesis. If the limit as n goes to infinity of a sub n is not equal to 0, then the series diverges. That's it. Very, very simple. Now, in terms of applicability, this is a 4-star test. It applies to any series, no problem. It's easy to use. You just take the limit of the nth term as n goes to infinity and check whether it's 0 or not. But in terms of overall usefulness, well, this is very limited in the sense that it only tells you one thing, whether the series diverges. If that limit is equal to 0, well, you don't know anything. What do I mean by that? Let's look at some examples. If we consider the sum from 0 to infinity of 4 to the n minus 3 to the n over 4 to the n plus 2 to the n, let's check it. The limit as n goes to infinity of the nth term is, after a little bit of factoring, the limit as n goes to infinity of 1 minus 3/4 to the n over 1 minus 1/2 to the n. Well, 3/4 to the n and 1/2 to the n both get very, very close to 0. Therefore, this limit is 1, which is decidedly non-zero. Therefore, this series diverges according to the nth term test. So far, so good. What about the series? As n goes from 0 to infinity, -1 to the n over n factorial. Well, if we take the limit of a sub n as n goes to infinity, we get either plus or minus 1 in the numerator and n factorial in the denominator. That is definitely 0. And indeed, this series converges. We know that this is e to the x for x equals -1. Simple enough. But what about the harmonic series, the sum of 1 over n? Well, if we take the limit as n goes to infinity, we get the limit of 1 over n. That's equal to 0. But wait a minute, we already know that this series diverges. What is wrong? Has our test failed? No, our test has not failed. Your logic has failed. If you have a logical statement of the form, if P, then Q, then you cannot conclude if Q, then P. That is called the converse, and the converse does not always hold. In our nth term test, we have the limit as n goes to infinity of a sub n non-zero implies divergence of the series. Divergence of the series does not imply that the limit of the nth term is non-zero. The converse does not hold. What then does hold? What can be said? What can be said is the contrapositive. P implies Q is the same thing as saying that not Q implies not P. We have to negate both statements and then reverse the arrow. That contrapositive is always true. So, what we can say is that if the series converges, the negation of divergence, then the limit, the nth term, is zero. The contrapositive will hold.
So, if you follow the rules of logic, you won't get lost. Or, if you do get lost, it's because you've not followed the rules of logic. In our next two lessons, we'll begin introducing specific tests for measuring convergence and divergence of infinite series.